Good evening. I'm not with you tonight, so I'm broadcasting from my little den. Tonight, we welcome our speaker, Phil Bull, who's a cosmologist at the Jodrell Bank Centre for Astrophysics at the University of Manchester. He's originally from Stoke-on-Trent, and he worked and studied in Manchester, Oxford, Oslo, and at NASA's Jet Propulsion Lab, also the University of California, Berkeley, before returning to academic positions at Queen Mary University of London and then on to his present position in Manchester. Phil's research covers theoretical and observational cosmology with radio and optical telescopes, particularly using very large galaxy surveys and observations of the radio emissions of neutral hydrogen across most of cosmic history. So let's give a big Mexpert and Swinton welcome to Phil Bull. Thank you.
Thanks, folks. Can you hear me okay still? Yeah, great. So I'll try and share this. How about that? Can you see it all right? I might have to move some stuff out.
Yeah.
All good? Right, shout up if you can't hear me at any point. So, thank you very much for having me. I'm sorry I can't be there in person. It is a bit of a long round trip for a school night, but Zoom's all right, I hope. So, yeah, and thank you for the for the introduction. It sounds like I've got a lot of air miles the way you said it. So, thank you for that. Tonight, I'm going to talk about the cosmic dawn. And so this is an era of the universe's history that's sort of what we call when the first stars and galaxies are forming. So before then, the universe was pretty dark. There weren't many ways for light to be emitted by anything, no stars or galaxies yet. But then these first objects really lit up the universe and started to affect all the stuff around them. And this sort of paved the way for the universe as we see it today. So I'm talking about a period of cosmic history that's sort of a few 100 million years after the Big Bang, when nowadays we're sort of about 14 billion years after the Big Bang. So it's really the infancy of the universe that we're talking about here. Right, so if I can make the slides go. What I'm really going to be talking about is galaxies and where galaxies come from. Okay, I'm going to be talking about the first galaxies, and so as I'm sure you're all aware. So a galaxy, if you think about it, is the things we mostly see ourselves are the stars. You also see a bit of gas and something that blocks the light is dust within the galaxy, and so this is a particularly nice example of a spiral galaxy here, and you can sort of see this thing is sort of clumps of stars, gas and dust, and it's all bound together by gravity, right? So gravity is the force that dictates what happens on these very large distances that we encounter in astronomy and astrophysics. There's a lot you can't see as well. So by mass, this galaxy we're looking at right here, probably in the region of 80% of it, maybe a bit more, is in dark matter that's invisible. So we don't see any light that comes from it, and it doesn't absorb light either. But we can see its influence. We can see its influence because we can check how fast the stars are moving within this galaxy. We can see how the galaxy bends light as it passes through it from other background galaxies, and that's all consistent with the majority of the stuff that we can't, that's in this image. Most of that stuff we can't see. It's dark matter. Okay, but all of that stuff sort of comes together and is bound together by gravity, and sort of that's the main driving force for how you get these nice spiral galaxies. And in fact, the force that is causing the stars to glow, the gas to clump together, and ultimately is responsible for how the dust got there as well. So we're all very big on gravity. And then again, as I know you must be aware, there are all sorts of galaxies. And hopefully you've seen a good fraction of the ones I've shown here, either in images from the Hubble Space Telescope or maybe yourselves directly. And so you can see here, it's not just spiral galaxies. You can see barred spiral galaxies. There's these nice, more complicated looking ones. I think you can probably see where my mouse is. I'll just assume that you can. But you get these things like galaxy mergers, two galaxies passing very close to each other, and they sort of get drawn in mutually by gravity. And that causes a big burst of star formation and disrupts the shape of the galaxy. And all sorts of weird and wonderful shapes. And we, as astronomers, try to classify them and use that classification to learn something about the physics behind how these galaxies are formed and what we think they're going to do in the future. So the sort of classic three types of galaxies are spiral ones. You can distinguish between spirals with bars or just spirals on their own. Elliptical galaxies that astronomers tend to think of as red and dead galaxies. Ones that any spiral structure they may have had has been sort of dispersed and disrupted, and you just see a sort of hazy glow that's mostly a reddish colour instead. And irregular galaxies which have been disrupted or were too small to form into more pleasing to the eye shapes. Things that look a bit more chaotic, like these types of irregular galaxies. And then we can also distinguish between them based on what their predominant colour is. We think of blue or bluish galaxies as having more star formation going on. Reddish galaxies as having more older stars. You tend to find that new star formation gives you a lot of blue light, blue and white colours, and a lot of older stars tend to be more yellowy or red, and so that's another way we classify the galaxies as well. And then beyond that, we can talk about galaxies as we see them at other wavelengths. So I'm a radio astronomer by trade, so we look at things like quasars. So these are galaxies that are dominated by the light that's emitted from around a central supermassive black hole, for example. But the point is, there's all sorts of galaxies, and there's all sorts of different physical processes going on them, and that's intrinsically interesting to someone like me. So here's a test for you. What are these galaxies called? So I've said there's all sorts, spirals, ellipticals, etc., etc. These are some of the more weird and wonderful ones. So I don't know how the audience participation will come across on Zoom, but does anyone want to have a go at giving this galaxy a name on the left?
Irregular.
Yeah, I think I'm hearing dolphin.
Dolphin galaxy.
Yeah, you wouldn't be far for that. Could be a goose or something, maybe a peacock. I don't know. How much are you willing to squint? That's the question. What about this one in the middle?
Jellyfish.
Yeah, that's pretty jellyfishy, isn't it? I don't think anyone gets any prizes for the one on the right.
Question mark.
Yeah. So yeah, so I don't know why they've gone for porpoise instead of dolphin, but they have. These are so this is the porpoise galaxy because it looks like a porpoise. This one is a type of galaxy called a jellyfish galaxy. So we actually see a lot of galaxies like this. So the one on the left is just it's been disrupted because of this massive elliptical type galaxy just below it, and you can see what's happened. So it looks like it was a spiral galaxy, and then it sort of got shredded by the tidal forces from this big galaxy here. You can see all the galaxies and stuff in the background, they aren't part of this, but you can sort of see these lines of blue light, that sort of star formation that's been triggered by this shredding process, this disruption process. You can see these dust lanes within the galaxy have become detached, but it's still sort of got most of its spiral structure. It's gotten really hazy though, So this is a galaxy that's sort of been torn apart by getting too close to a more massive galaxy, and that's why it has such a weird shape. With the jellyfish one, there's some physics going on there as well. This is again a relatively normal spiral galaxy, but you're getting these big streams of material off here. They're very faint. You wouldn't see this apart from with a space telescope, essentially. This is extremely faint stuff, but we can see it with something like Hubble. And what's happening here is that there's another galaxy sort of out of shot of this particular image, and lots of material is sort of being blown off that galaxy by various processes going inside it. It could be lots of star formation and stuff like that. So this other smaller galaxy is sort of heading into a wind, right? A wind caused by some other galaxy, or maybe a few galaxies, and that's sort of blowing some of the gas and dust and even stars out of the galaxy. So what you're seeing with these streamers here is actually, some pool of people, their solar systems have got kicked out of the galaxy. So that's not where you want to be necessarily. But you get these very beautiful sort of tendrils that are many times the length of the actual galaxy itself. And this is stuff being blown out of an otherwise normal galaxy. This one, I mean, it's just an accident that it looks like this. I think that there's probably some interaction going on between two galaxies here, and just the way it's lined up, we see it like a question mark. So I don't think there's anything particularly interesting physics-wise going on there, apart from two galaxies are interacting with each other. But like I said, there's all sorts of galaxies, all sorts of weird and wonderful out there. Some colleagues of mine have made an alphabet out of images like this, so I haven't shown it here, but you can choose any letter of the alphabet you like, and you'll find a galaxy of that shape somewhere. And this is made possible by the fact that we're now doing surveys of galaxies, so taking many images over many nights of the night sky in different coloured filters, and we now have catalogues of hundreds of millions of galaxies. So it's no surprise that we'll find quite a few weird and wonderful ones during that process. And anyone who's had a go of the Galaxy Zoo website or any of those projects, you're seeing a good sample of some of those images. And hopefully you've seen some interesting ones in there if you have done it. Okay. So hopefully I've convinced you that there's a lot of galaxies out there, and they've got all sorts of interesting stuff going on. But how do you make a galaxy in the first place? And so we do have to go quite far back in time, and you first have to invent the universe, right? You can't have a galaxy without a universe with stuff in it that a galaxy can be formed from. And so this is my very brief history of the universe. So we'll start with the Big Bang, or the thing we call the Big Bang. People like to talk about singularities and stuff like that with the Big Bang. We don't necessarily need any of that. All we in cosmology, what we mostly mean by the Big Bang is there was some initial state of the universe where everything was hot and squeezed together, and then from then on the universe started expanding. Right? It doesn't sort of matter what happened right at the start, as long as everything was squished together. Very early on, all of our models of the universe make sense as long as the universe looked like that way in the past. So space itself is stretching. So since whatever time we use as the sort of start of our universe, space itself has been stretching. That means everything has been getting further apart from everything else. This causes it to cool down. Okay, so it's all hot and squeezed together, but it's expanding, it's drifting or stretching apart from other stuff. It cools down and it expands. And so as time goes by, you go from a universe that's full of hot stuff, hot gas, particles, stuff like that. It can cool down, and sort of normal matter can form, essentially, once the universe gets cool enough. After that, we reach a time, I've skipped a few steps here, but we reach a time that we like to mysteriously call the Dark Ages, and we very literally mean the Dark Ages. So after a while, space has stretched enough that it's filled with cold gas now. Cold gas everywhere. There's dark matter and stuff as well. We're not worrying about that for now. But it's filled with cold gas. This is the gas that's literally left over from the Big Bang. Okay, what we call primordial or pristine gas. Nothing's ever happened to it much. It's never been through a star. It's never, been part of a planet or anything like this. This is clean, unused gas, mostly hydrogen, from the very start of everything. And that's it. That's what's going on at that time in the universe's history. We're talking sort of 1 million years to 100 million years after the Big Bang. There's no stars yet. There's no galaxies, and so nothing is shining. So there's no light. Space itself is just full of this cold gas that's dark. It's not emitting any light. So if you were around during the Dark Ages, you wouldn't see much. Okay. Fortunately, gravity is doing its job. It starts pulling gas together into clumps. If you've got a bit of the universe that has a little bit more gas than some other bit, then gravity tends to, there's a sort of snowball effect. That gravity pulls in more and more stuff. Right, gravity attracts stuff. The more mass you have, the more attraction you get of the surrounding stuff. And this pulls the gas together into clumps. But eventually, you get clumps that are big enough and that have been squeezed together enough by gravity that they get hot and dense again. So not quite like it was in the Big Bang, but back to a hot and dense state, and they can start nuclear fusion and become stars. And so at some point during the Dark Ages, the first star will have formed, probably the first stars. That's a process that went on all throughout the universe, and then we started getting an appreciable number of stars. The universe was lighting up again. Okay? And then, with time, enough stars form, and gravity has enough time to act, that these stars will start to clump together into big complicated structures. So, first, what we call proto-galaxies, pretty irregular shapes, blobs, essentially, made up of clusters of stars, and eventually forming more and bigger and complicated structures. So at this time, this isn't sort of like the star formation we see today, where you'll have a cloud of gas, a molecular cloud. It'll collapse and fragment into multiple stars, so like a stellar nursery, like the Orion Nebula, and then over time those stars will drift apart from one another. It's sort of, you have stars forming all over the universe in different places. That's the picture here. And then they clump together because of gravity. And then the modern era, of course, the highlight of that. So normal galaxies that we see today, and the sandwich was invented in this period of time, very importantly. And so this is it. This is the universe we're left with. We've got stars, we've got galaxies. Around those stars, planets have formed. Lots of other stuff going on in between the stars, the interstellar medium as we call it, but again, most importantly, the pinnacle of civilization, sandwiches. So, as part of this picture of how stars and galaxies form, and subsequently us, it becomes apparent that we, and everything you see in front of you, everything I'm looking at in front of me, more or less, was made out of the processed material that has previously been in a star. So if it's hydrogen and actually helium as well, those were elements that were made in the Big Bang. They've been here for the whole time. Okay, it didn't take too much to make those during the Big Bang, but other elements weren't there. Maybe tiny traces of some things like lithium, but all other elements are made inside stars. So if you think about the iron in your blood, or the oxygen and nitrogen in the air, or things like that, these are all materials, these are all elements that have literally and necessarily been in a star before. Okay, there's no way of forming them otherwise. The hydrogen that's in, the hydrogen in the water that's in our bodies, yeah, that's from the Big Bang. But otherwise, the oxygen in that water, it's got to have been through a star. Depending on the elements you're looking at, some of those elements are byproducts of nuclear fusion, so they just formed while the star was doing its normal star things. It was, burning or fusing together hydrogen or possibly some other elements. And they're just made normally in the star. And when the star dies, those elements get chucked out into a galaxy where they can eventually, over time, clump together again and form a new star or new set of stars and new planetary systems around them. So our Earth and our solar system, roughly 4.5 to 5 billion years old, obviously less than half the age of the universe. For us to be here and for our planets to have formed and ourselves to have formed, there must have been previous generations of stars that formed and subsequently died, flinging their material off into space, either through planetary nebula or a supernova, and then some of that material has made its way back into a new generation of stars, like our sun, and around that, the sort of gas and dust has been able to, that's left over from the star forming, has been able to clump together and make planets and ourselves. All of this is, processes that take hundreds of millions to billions of years, so absolutely unfathomable timescales. But it has happened, and it seems to be the only way it can happen. So we're literally made of stardust in this very real sense. Some heavier elements don't just need to be made inside a star, they need to be made at the point that a star has a very violent end through a supernova explosion. So roughly anything heavier than, or denser, I should say, than iron, so things like, uranium, for example, had to have been made when a star didn't just die, it exploded. So other things we find on our planet aren't just from regular star life cycles, leaving over there, putting their byproducts out into the galaxy. They're literally things that could have only been left out in space by another star having a very violent death. So that's fun. We don't think there's just been one generation of stars before us. We think there might have been several. And the reason we think this is we know, and we can work out from physics, how long stars should live for. And it depends a lot on their mass. The more massive they are, the faster they burn through their fuel, so the shorter their lifetime. And they tend to be brighter and bluer as well. The most massive stars tend to go supernova at the end of their lives. These are the O and B class stars typically. And new stars form out of the material they leave behind. And so what we see in galaxies today, like the nice image I'm showing you here, is you can see active star formation going on. You've got these sort of, obviously this is a multicolour photo with some spectral line in, O3 maybe. But these pinky colour things are where there's very active star formation going on. That's a new generation of stars being formed right now, but the sort of other colours you can see in this image, previous generations of stars, and even those stars are probably second or third generation. So practically none of these, possibly none of these at all, are the first generation of stars. Okay, so what we see today is a result of a very complicated and lengthy generational evolution process of stars and galaxies that relies on other stars and galaxies, or certainly other stars, having formed before. So the stars we see today are here because there were previous generations of stars. But that doesn't help us understand how the first stars and galaxies formed. There had to be an original set of stars and galaxies, right? So this is where things are getting increasingly exciting, because these are questions we've had in astronomy for, well, an extremely long time, and we have our thoughts and our theories and our predictions for how stars and galaxies should have formed in the first place. But now, thanks to this beautiful and expensive piece of machinery, the James Webb Space Telescope, we're able to start answering some of those questions for definite. Okay, so well, this is a bit of a fancy artist's impression sort of picture, but it looks cool, so I used it. Here's a sort of scale model, and some of the scientists who worked on construction. It's not deployed on a lawn. It is up in space, I promise. And the sort of two key parts of JWST compared to the Hubble Space Telescope that make it really, really suitable for answering these questions about cosmic dawn and the first stars. So the first is, as you can see, it's got a much, much bigger mirror than the Hubble Space Telescope. I'll show you something for scale at some point. But you know, if you think about these hexagonal patterns, that it's useful to have it in this interlocking way, so you can sort of fold it out and deploy it. It needs to fit into a rocket at some point, which it did successfully, and then deploy. So anything in space that needs to be deployed is always scary to space engineers. But when they came up with the design of JWST, it was complicated, but they talked to the contractors, and the contractors were eerily confident that they could do it, which we take to mean they'd done it for military purposes before, and it was classified. So JWST has always been something that we sort of knew we could do, but unfortunately it had cost overruns and delays like many mega projects end up getting. I won't mention HS2 being where I am in the country. But the point is, it's much bigger mirror than Hubble, so it can see fainter things, we can see further back, we can see stuff that's light that's travelled further distances, essentially. And another important point of JWST is it's more sensitive to infrared light than the Hubble Space Telescope. That's just the choice of cameras and filters that have been used, but very importantly, this means it can see through dust and other haze out there to look at stars as they're actively forming, and also stars and galaxies very far away, where their light has been stretched or redshifted by the expansion of the universe, and so galaxies that are further away look much redder, and so we were very sensitive to them with JWST because of the choice of wavelengths it works at. And just some numbers for the aficionados. So this mirror diameter is about 21 feet. Hubble's is a mere 8 feet. And of course we're in space, so the seeing is great up there. So what do I mean when I say it's working in the infrared? This is your standard spectrum plot. So visible light, if we say visible light is here, sort of hundreds of nanometers. That's what Hubble can see. Hubble actually sees a bit into the ultraviolet and the infrared, which is great, but JWST goes really far into the infrared, and so that's why we can use it to sort of see through dust and gas and look at these very distant galaxies. So this leads us to the question of, can we see the first galaxies forming now? And we do need a bit of help with that. So in this image, this is quite a cool image, I think. So you can see this is the image sort of zoomed out a bit on the left. There's a huge galaxy, a huge elliptical galaxy here on the left where my mouse is. And you can see there's sort of these funny, sort of almost like arc shapes here. This huge galaxy is bending the light as it travels past it, so it's acting as a lens, a gravitational lens. And so if we zoom into parts of this image, we can actually see the sort of images of galaxies behind this big galaxy that have been lensed and magnified by a very great factor. Now, because of this lensing effect, it's not like it's a perfect magnifying glass or something that gives you a beautiful image. This is just, we're seeing stuff almost at random because it happens to have been in the right place to get magnified, and so we often get this stretching or distorting effect, right? But the nice thing is it's magnified, so even if it's very far away and very faint, we can now see it a bit more easily because it's been made brighter by the fact that it's passing through this sort of magnifying gravity of this big galaxy. This is the gravitational lensing effect that was predicted by Einstein and successfully observed, and that's why everyone's so happy with Einstein, because he made a prediction and it came true. So the important thing for us today is that it lets us see very faint galaxies, much fainter than we'd be able to see unaided, merely with JWST, but the problem is they look stretched. But what we can do is we can work out essentially the pattern, the shape of this lens using optics, essentially, to sort of undo this distortion effect. And so this is what we get if we try and undo that distortion. So we unstretch and we optically figure out where the light rays have been going, and we would see this. So this is a sort of computer model that's based on the data you just saw. It's based on the image you just saw, and we've sort of unstretched it. And this is what we would see if we'd done a good job of unstretching it. We see all these stars, clumps of stars in the very early universe coming together for the first time. So they're all different colours and stuff like that. So some quite pleasing colours here, really. You can see this haze, this sort of diffuse gas stuff behind it as well. We can even see that. It's very faint, but it's been magnified. And so what we're actually seeing here is not the first galaxy, or one of the first galaxies. This is a very early galaxy in the process of forming. So it's been caught red-handed, essentially, or yellow or blue-handed. But what we're seeing is a proto-galaxy coming together. Clumps of stars have formed, and then those clumps of stars are being pulled together under the mutual attraction due to gravity, and then this is what we can see in this image. And we can only see it, because this is very faint and very far away, but we can only see it because of this gravitational lensing effect. We're astronomers, right? We have to give things stupid names. This is called Firefly Sparkle for some reason. I guess that's an appropriate name, but what we're doing is, that's just for the newspapers, isn't it, really? It's probably also got a very long and boring numerical name, so I should have put that in instead. But we're seeing it as it was forming 570 million years after the Big Bang. Okay, so this is a very early galaxy caught in the act of forming, and that's something we've never seen before. So we can try and push this further, right? So this is more like it. We've got a nice semi-lengthy name. This is Jade's GS-Z14-0, and this is one of the most distant galaxies we've ever seen. It's seen by the Jade survey, which I think was on JWST. Imaging done last year, and what you can see here so JWST takes these beautiful images, quite large patches of sky in a sense. There aren't many stars in here, so this is a star. I think there might be one or two other stars here, and you can see this nice sort of six-fold, what we call the point spread function, this pattern here. That's because we have the hexagonal mirrors. So because these are hexagonal mirrors, you see this pattern for the stars instead. They're very bright and point-like. All these other dots, literally all of these other dots in this image, are distant galaxies. There are thousands, tens of thousands of galaxies just in this one image of a sort of smallish patch of the sky where there's only a couple of stars from our own galaxy. Okay, so if you've ever seen the Hubble Ultra Deep Field, they pointed Hubble specifically at an empty looking patch of sky, observed for a long time. They saw so many galaxies. This is sort of, normal observing for the James Webb Space Telescope. We're seeing so many galaxies here that you could barely even count them. And they are literally all galaxies. I'm not even going to try and zoom in to a lot of this stuff. You can see they're all different colours as well. There's a nice red looking one there. That suggests it's very distant. There are some more yellow looking ones. They're probably not they won't be as distant. You can see some bluish ones here that are probably in the local universe. I don't know how well you can see this on the screen there, but it's worth looking it up because you could easily get lost in this image for an hour or two. There's so much stuff going on. Anyway, a particularly tiny corner of this image we can zoom into and see this very, very red object, suggesting that it's been redshifted greatly, and what we're seeing is a very distant galaxy indeed. And so this is this JADES GS Z14-0, and we can run the numbers, figure out how far away it should be, figure out what its redshift should be, and use that as a proxy for its distance. And we're seeing a galaxy here, we've confirmed, as it was only 290 million years after the Big Bang. So really must be one of the very earliest galaxies in a sense. Do we expect to see galaxies so early on in cosmic history? This is a relatively bright galaxy. There must be a lot of stars within it. How did it form so quickly? So we expect to see little blobs of stars like we just saw, that Firefly Sparkle one. But how could it have all sort of formed into quite a large and bright galaxy, large and bright enough that we can see it after all this time, over all this huge distance? It's still bright enough to see with JWST. This is a very big galaxy that must have formed very quickly. How long does it take gravity to pull together stars? Well, apparently, 290 million years is enough to form a pretty big, irregular-ish shaped but still very bright galaxy. Sort of on a related topic to this, we've been seeing what we call little red dots, and these are still a bit of a puzzle. Okay, why little red dots? Well, they're little and they're red, so these seem to be objects that are very far away. That's the reason they're red, because they've been redshifted. The stretching of space has stretched the light into red wavelengths. And we just see lots of them with JWST. So this is one example. We can see, this is quite faint in a sense, because you can see all this background noise here, but it's still bright given the distance it must be at. For us to be able to see it quite clearly on this noisy image. And we see tons of them, actually. At least a few hundred have been seen so far. And again, we can see, lots of the background noise here in a couple of filters. But you can see they're all little, they're all red, they're all dark. You can't see any structure. Okay, you might be able to convince yourself, oh, there's like
Bill, it seems that we've lost contact with you at the moment. So if you'd like to stop talking and try and reconnect.
Oh, did I lose you for a bit?
We got to lots of little red dots.
Okay. Can you see the red dots now?
Yes, we can.
Yeah. So I'll just go back a little bit. But essentially, we're seeing lots of these. We can't see any structure here. Any structure that you can see in the image is just due to the telescope optics. So they are genuinely like dots. They're not spirals or ellipticals. And so as far as we can tell, they must be quite small or compact objects. And so, for the distance they're at, they're something potentially quite unusual. Even at these distances, we think we'd be able to see if it was a spiral or an elliptical type galaxy. This is something else. And there's lots of them. And they're very far away and they're very bright. So what are they? Even weirder, we see them appear after about 650 million years after the Big Bang. So I don't think any have been found before this time, not so far anyway. And then after about 1.4 billion years, we don't see any more. And even weirder, we've never seen one of these with the Hubble Space Telescope. So Hubble has been looking and making very, very deep images for a long time, and we never saw these with Hubble. Okay, these are new to JWST. We're only seeing them now. What is it about them that means we're only seeing them now? And what is it about them that means they weren't there right at the beginning, but they're not there anymore in the universe as we see it today? There's something interesting going on here. So these are the questions we have. So they're very bright. If they're made of stars, which we think they must be somehow, could so many stars have formed so quickly to make something this bright? Why don't we see them today? So these are presumably lots of stars. They're not supernovae or anything like that. Supernovae get dimmer after a few days. These must be galaxy type objects, right? They're persistent. They're there. They're not fading or anything. So these must be sort of collections of stars or something. But we don't see any today, so they must be different to the galaxies we see today. A different type of galaxy, a new type of galaxy that only existed in the early universe. And then there's so many of them. They seem to be common back then. So is this just a normal phase of how galaxies form? Perhaps all the galaxies we see today went through a phase, a little red dot phase, or maybe some large fraction of them did. So is this part of the development process of a galaxy? So here's a picture of what we think could be going on, but it's not conclusive yet. So we think what we might be seeing is supermassive black holes that are formed very quickly. That's still a big puzzle. How they could have formed so quickly in the early universe, we don't know. But if they did form very quickly, they might be shrouded in dust, essentially. Dust from a earlier generation of stars. And what that would do is obscure them from telescopes like the Hubble Space Telescope. Right? It would absorb the light at the wavelengths that the Hubble Space Telescope is sensitive to. And even though these are very bright, a lot of the light has been created not by stars in this case, but by an accretion disk, so a swirling disk of matter that's been drawn into the black hole, and all that matter sort of gets heated up as it swirls around. That produces an extremely bright light, but that's somehow getting blocked, so there must be a lot of dust to block it to Hubble, but James Webb can see through dust. And so that's why we see these bright red objects, we think, these little red dots. And so why do we only see this in the earlier universe? Well, we think maybe these black holes must have been feeding in a different way than they feed today. So if galaxies earlier in history were very compact and there were stars close to the centre, many more than we see today, that would have fed the black hole very rapidly. You've got lots of food on hand, essentially. That would have produced a lot of light, and by destroying these stars that are nearby... Oh, did I lose you again?
No, we're still here.
Oh, you're still here. Sorry, I got a message on Zoom that said unstable. Good, I'll keep going then. We think this material, this nearby material, fed the black hole, made this really bright light emission, and the stars getting shredded up would have produced gas and dust that would have been flung out into the rest of the galaxy and obscured what was going on in the middle, which would explain all of these things that we observe. Later on, these galaxies still have supermassive black holes, but they're feeding much more slowly. There's not as much material nearby. So because early galaxies must have been quite dense, later galaxies aren't as dense, they're a bit broader and puffier. We don't see the little red dots today. This is what we think could be happening, but there's still lots of loose ends. These black holes must have gotten big very quickly, and we don't even know if it's perhaps physically impossible for them to have gotten this big, this fast. So this is a very active area of research. Okay, so just to finish off, for a few minutes, I'll talk about hydrogen because this is something very close to my heart. I mean, literally, but also figuratively. So the first stars formed from primordial hydrogen gas. Okay, this pristine gas that I mentioned at the start. Could we just try and see that gas? Maybe that would tell us something about how these first stars and galaxies formed. And so the question I'm asking here is, can we look back somehow to the Dark Ages? And that seems a bit silly in a way, because the Dark Ages are the time when there was no light. Nothing was giving off light. There's nothing to see. It's dark. So with JWST, there's no point. There's no point trying to observe stuff that happened in the Dark Ages because there's no light for it to see. There's no stars, there's no galaxies. So at the wavelengths JWST works at, there's nothing to be done. But, fortunately, hydrogen gas does emit very weakly in the radio part of the spectrum. And so this is the 21 centimetre wavelength emission line from neutral hydrogen, which radio astronomers spend an inordinate amount of time trying to detect, including myself. So if you've got a radio telescope, you can tune it not to a wavelength of 21 centimetres, that's about 1.4 gigahertz for anyone who's into radio, not far from Wi-Fi or mobile phone signals, but we don't tune it, to see this stuff we wouldn't tune it to 1.4 gigahertz, we'd have to tune it to much lower frequencies, because we're not trying to see the hydrogen gas as it is today, we're trying to see the hydrogen gas from very early in the universe's history, and the wavelength of that gas has been stretched. So that's made it go to lower frequencies. And so due to this stretching, this cosmic expansion, this redshifting, we don't expect to see the hydrogen gas from the Dark Ages at 1.4 gigahertz anymore. We expect to see it at roughly 100 megahertz and below. So that's below the FM band, significantly below radio 2. How can we try and observe that? Well, a really big effort, and the global headquarters of this is actually at Jodrell Bank, which is fun. They've got a nice cafe. Is the Square Kilometre Array. So this has been an idea that's been around for several decades now, and we've broken ground. We're building it. We're building it quite quickly. It's an array of hundreds of thousands of antennas. The ones I'm showing you here, this is a mock-up in the Murchison region of Western Australia. So it's out in the desert in Western Australia, essentially, and we connect all these antennas together, put all the data into a gigantic computer, and we can use that to make quite nice maps of the hydrogen gas through this neutral hydrogen, this 21 centimetre emission line that lets us see, where is the hydrogen on the sky during the Dark Ages and as we go through to cosmic dawn. And what we're really looking for here isn't the gas itself, we'll see that, but we're looking for bubbles within this gas, because what happens if the first stars and galaxies are forming... Oh, am I still audible?
Yes, I can still hear you. It's not
good.
Transmission.
Okay, good. So we're looking for bubbles where there isn't any hydrogen or neutral hydrogen. So what happens is, around the first stars and galaxies, they're very bright, they emit lots of ultraviolet radiation, essentially, and what that does is it slams into the neutral hydrogen and liberates it of an electron. It ionizes it, so it changes it from being this cold gas that's emitting at radio wavelengths into hot gas that's emitting in visible wavelengths, but not in the radio anymore. If you ionize hydrogen, it doesn't emit in the radio anymore. So what we're actually looking is for these bubbles or voids where there isn't neutral hydrogen gas anymore, there isn't the cold gas, which implies it must have been heated. And so these bubbles we would see would tell us where the first stars and galaxies were forming, because they're producing all this UV radiation that would be destroying the radio emitting gas that we're sensitive to. Before SKA, the Square Kilometre Array, comes online. That'll be a few years yet, but progress is good on building that. You can do something much simpler with what looks like a glorified but very strange table that my wife certainly wouldn't allow us to put in the back garden. But this is a telescope called EDGES. It's a type of radio antenna called a blade dipole. So these two shiny things you can see here are bits of metal, aluminium panels essentially, and acts as an antenna. And this is a type of antenna that can't see the bubbles or anything like that. It doesn't have the resolution, but what it can do is measure the total temperature of this gas. So essentially, instead of trying to take pictures and look for these bubbles, we can do a much coarser and simpler experiment, which is just trying to measure its temperature and how that changes, how that changed with time, which is the same as saying how did it change with frequency, because different frequencies are light from different, emitted at different times in the universe's history. They've been redshifted by different amounts. And so the point here is, by measuring the temperature, you can see what's going on. Is the gas being heated up or being cooled down? And the first stars and galaxies can cause both things to happen. They can borrow energy from this gas, or they can heat it up as things go along. And so we can use this to try and see, if the first stars have started forming at a given point in a very coarse way. So as long as we tune this to the right frequency, we would expect to see a dip in temperature as the first stars form. They're sort of taking energy out in a way. So that's what we're looking for. And this EDGES team, the thing you can see on the screen right now, they claim to have got a detection of this, but it's highly disputed. We think they might just be seeing the ground, and they haven't corrected for it. They're very careful and meticulous people, but it's such a hard measurement to make. We just squabble about it essentially. Well, part of the reason for that is we don't believe that the result they've got is possible. Okay, so the gas that they see, if they are indeed seeing it, is much colder than you would expect. We don't see how it could have possibly gotten as cold as this would imply, and that's why we think they might have got something wrong. Now, of course, it's fun to squabble and snipe at other people, but you've got to sometimes put your money where your mouth is. And so we're trying to build our own experiment at Jodrell Bank. Rather than this sort of blade dipole, this funny table in the desert, we're building a big horn-shaped antenna. It's called Rhino, because it's a big horn. And this thing is much bigger. It's about 24 feet high. And the idea and the reason it's a horn is because we think we can make even more careful measurements of this temperature, and we can control those measurements better by using this horn-shaped antenna instead of those aluminium panels. And so this is a sort of watch this space. This is something we're actively building, and every week when I go to Jodrell, I have to get on at the welders, because this is quite a big job to weld. It's about 52 panels. Okay, so let me just sum up here. Do we understand cosmic dawn? And the answer is not yet. So we've got lots of interesting clues. I've shown you little red dots. I've shown you that this James galaxy, very, very distant. I've shown you the Firefly Sparkle proto-galaxy. We've got this unusual cold neutral hydrogen result that no one quite believes yet. There's obviously something going on, and we don't have the full picture yet. But it's important to get this picture. We're genuinely talking about the story of how life itself got here. We're talking about our own cosmic origins, right? This is sort of the biggest and oldest story in town. So it'd be very nice to sort of finally complete that and really understand how the first stars and galaxies got here, how subsequent generations got here, and then ultimately how we came to be. And this is an exciting time for this stuff. It's the theories we have for all this stuff are constantly being rewritten. We're seeing science in action. There are new publications, new scientific papers every day on some of these topics, and it's confusing right now. But thanks to the James Webb Space Telescope and other instruments, we've got all this nice data to really give us a headache, and it's going to let us figure out the answer to some of these questions with a bit more time. So I'll end it there. Thank you very much for your attention, and I'm happy to answer questions if there are some.
Bill, thank you very much. What a lot of information, and I'm sure we're going to get some questions. I've got a few myself if other people don't bring up the points. Could I ask you to stop sharing your screen? Yeah. And we'll go back to the gallery. So if you have a question you'd like to ask Phil, if you're in the room, just get my attention. If you're online, a digital hand, please. So I'm looking for questions. To start off with, then, while people are framing questions, going back to your red dots and your explanation about a super-sized black hole at the centre of those galaxies. Is there enough time between the start of from the start of the Big Bang to 650 million years to create such a large black hole in the classic mechanism, or is there another mechanism happening where we don't see a stellar formation?
Yeah, that's a great question, and it's one that's got all the theorists arguing essentially. So there can always be several things going on. So we think that we might be measuring these things and getting their mass a little bit wrong, or getting their brightness a little bit wrong. It's right on the edge of what's physically possible. So for black holes to form, you have something called the Eddington limit. And this is where if you try and feed a black hole, so you put material in that will make the black hole grow in size or mass, that will pass through the accretion disk that is very bright. And if your accretion disk is too bright, it'll sort of, through radiation pressure, so it'll be so bright it blows the material back again. Okay, and it won't be able to feed. So if you have a black hole that's feeding too fast, it will limit itself. It'll push the material away. And so this Eddington limit seems like quite a fundamental thing. How can you get around it? Some of these black holes might be too big to have formed at the Eddington limit, the maximum speed you could form or grow one of these things. Some of them might be a bit beyond that, but we may have also measured the mass slightly wrong, and it's just about under this limit. So we don't know if it's possible yet. Maybe something interesting is going on, and you'd have to have some new unforeseen process that causes these things to form. But that would have implications as well. If we just had smaller black holes forming but then suddenly colliding, we'd be seeing gravitational waves from those and stuff like that, perhaps. So we don't know. We don't know yet, but it's something that's a very active area of research.
Okay, thank you for that. Roy Gunson had his hand up first. Roy?
I enjoyed your talk, Phil. I've got a query. You mentioned those star clumps in that very, very early galaxy. I was wondering, are there anything like, say, a globular cluster? Because we know globular clusters are very old, 11, 12 billion years in some cases.
Yes, so these things we think must be much brighter and a much earlier type of star than what we see in globular clusters. But you're absolutely right that globular clusters formed very early on for our galaxy. So what the stars we see in a globular cluster aren't the first generation of stars left over, but they could still be quite an early generation. So I think this picture of these blobs as being like, is it anything like the Orion Nebula or any other sort of active star forming region? They look quite different, but a lot of the same physical processes are going on. Like the Orion Nebula is part of the reason it's beautiful is because you've got all this dust going on that gives you this sort of nice, these reflection effects and so on. There wouldn't be any dust at this point, not much at all. It hasn't had chance to form in stars. So these things will just be sort of like weird clusters of extremely bright, extremely massive stars that we call population 3 stars. And these are beasts. If the sun is one solar mass, these things could be hundreds. So like a globular cluster on steroids with a very short lifetime, because the big high mass stars go pop very quickly in a few million years typically.
Okay, thank you.
Gregory Magnet, online.
Yeah, great. Thank you very much. That was a really interesting talk. I just had two questions. On the gravitational lensing, I understand that I guess it shifts or lengthens the light and the z-score gets higher, like 10 or 14. But how is it magnifying the light? How does it appear brighter? And then I just wanted to ask you about the chemical composition of early galaxies. I know the Big Bang was light chemicals, like I think helium, hydrogen, some lithium. Is there a chemical difference between early galaxy formation and late? And can we use that to construct the chronology as well? I know, yeah.
Yeah, good question. So for the first one, there's two things going on. The universe is expanding, and then as well as that, we see this bending of light due to matter being here, like a big clump of matter. So that expansion is happening everywhere. It doesn't matter if you've got a big clump of matter or not. So we would see those distant galaxies being redshifted, so reddened very greatly, regardless. But this brightening effect, this magnifying effect, it is like literally, if we write down the equations to do it, which I will spare you from, but if we do that, it's exactly like a magnifying glass.
Yeah. Okay.
It's refraction. It's like a refracting telescope, right? It is literally acting like a lens. Why does that happen? Well, it's because we can think of what did Einstein tell us? Really, he told us that energy and mass are equivalent, and so we can think of the light that's traveling, whatever energy it's got, as if it like had some sort of mass, and then it's like sort of, then you can think of it like a billiard ball being attracted by gravity. It's not, it's light, it's traveling at the speed of light, but this equivalence between energy and mass allows us to say, well, actually, light gets deflected by gravitational forces as well, and that's what we're seeing. And it's a fantastically useful effect for us. The universe gives us a telescope for free, or almost for free. I mean, you still need your $8 billion mega space telescope or whatever, but it's very useful. So onto the chemical things. So yeah, these early galaxies, or certainly the early stars, the very first ones, they will be predominantly hydrogen and helium, probably about 75% hydrogen and the rest helium, tiny traces of anything else. That's one reason why they'd be so big and giant. There's no impurities in them. So other elements in stars like the Sun, that's still mostly hydrogen, but has lots of impurities in it, and that helps it stay smaller and cooler and still work like a star. So it gets a bit complicated to trace through all the reactions and stuff like that for the chemistry, but the point is these things are really like the most basic star you can possibly build. They've just got two components, hydrogen and helium, and so they look quite different to what we see today anyway. We can try and look at these stars or these galaxies and look at their spectra. Okay, so James Webb has a spectrograph on board, a very good one, called NIRSpec, near infrared spectrograph, and essentially that has been looking at these galaxies and seeing the spectral lines produced by different elements. And so I'm pretty sure we've seen these very distant galaxies. Some of them have oxygen, and some of the really distant ones don't. And that's quite cool, because that means it must be pristine gas, because we don't see any oxygen line in them. So yeah, we can definitely do a bit of it. It's hard; they're still very faint, but we can still see these emission lines and learn a bit about the chemistry of them, thanks to this giant space telescope.
I guess two follow-ups there. you mentioned it sounds like we're at the like 200 million year point for star formation. Is it, how much farther do you, or how much closer do you think we could get to the Big Bang? I mean, it feels like we're almost there in terms of seeing light. And then what is the earliest galaxy we've detected? I mean, you mentioned like pure oxygen. Do we know when the first galaxies were formed, or?
Yeah, so the first galaxy we don't know exactly yet, but that's what we're zeroing in on, right? But if I'd given this talk, 4 years ago, it would have been so different. I would have said, oh, the earliest galaxy we've seen was I think a redshift of 10 or something, which if you convert that is about a billion years after the Big Bang. So we've got almost a factor of 5 to 10 improvement, thanks to things like James Webb. We've got to keep going, but James Webb has a lot of lifetime left in it. Hubble's been up there for 30 odd years. We're hoping to get something, well, not quite the same out of James Webb, but quite a few more years. Another fun telescope just went up, yesterday morning actually, the Sphere-X telescope, which was something they were working on at the Jet Propulsion Lab when I was there. That's also going to be looking for very, very early galaxies and stars. There's a good chance they will see even earlier ones than we've seen as well. But yeah, let's see. It's very active. And I've forgotten your other question.
Just the chemical composition of galaxies. Again, similar to my first question, how much closer? If the Big Bang was 13.8 billion years ago, what's the oldest galaxy we've detected? Or
so the record holder's like between 100 and 200 million years old for now. We do see light from earlier times than that, which is the cosmic microwave background. So we do that's from only a few 100,000 years after the Big Bang, but it's produced through very different processes. There's no stars or galaxies yet. That's been produced because the universe is still warm, essentially. That's why we see the cosmic microwave background. That's been very carefully studied, and we've learnt a lot about the even earlier universe from that. But it doesn't tell us anything about the first stars and galaxies.
Got it. And Professor, last question. When you say expanding, technically the universe, we do believe it's accelerating, right? I know there's there, but yeah, okay.
Yeah, so it's expanding, and sort of we've known that since Hubble, so the sort of 1920s, and then noticing that expansion is getting faster is a result from the late 1990s now, and it's we've done our homework, we've made lots of follow-up measurements. I did my PhD on trying to explain this acceleration without needing dark energy or weird stuff, and you can't do it. We're stuck with it. So it's a very, very curious result, and I could give a whole talk on that as well. I won't. Don't worry.
It feels like, yeah, that'd be another great talk. That's like 95%, right? Dark energy and dark matter.
Yeah. So most of the stuff in the universe we think, and based on our measurements, we think is not visible and not normal stuff we're used to seeing on Earth. So we're very much in the minority, us lumps of carbon.
Well, hey, thank you. That was a great talk. Thank you very much.
Thanks for your questions.
Thank you, Gregory. Peter Lloyd, online.
Yes. Thank you very much, Phil, for a fascinating talk. I find I'm getting a little confused about the early timeline. I was under the impression, and it sounds as though I've got this wildly wrong, that the first stars formed about 1,500 million years after the Big Bang, but you're now talking about galaxies forming only 300 million years after the Big Bang. Have I got that star formation time just completely wrong, or was it at one time believed they didn't start till that much later?
Yeah, these are all new results. Sort of everything I've shown you today is hot off the press, not in the textbooks yet. Genuinely, a lot of the images I've shown you are from last year. They're less than 12 months old, some of them. So this is all new findings, new science, new stuff that's overturning the picture we thought we had. So the number you've got in your head isn't a bad number to have in your head. That was perfectly reasonable until the data has forced our hand now, and we think everything happened much faster than we originally envisaged. And the question is, why? What made it? The universe was itching to get going somehow. It could have happened at a much more leisurely pace, and we'd still get what we see today. But it wasn't. Everything seems almost rushed through, and there's no way out of that now. We're seeing galaxies, literal galaxies, bright galaxies, big galaxies with supermassive black holes and stuff, a couple of 100 million years after the Big Bang. So, yeah, it's really overturning all our theories about how stuff happened.
So when what I read was written, it was thought to be true, but it's more than 3 weeks ago. So we got it wrong in those days.
Yeah. So like I said, none of this is in the textbooks yet. I'm not even sure if it's in Wikipedia yet.
Information. Well, thank you for clarifying that for me.
No, thanks for your question.
Tony Morris.
You touched on the cosmic microwave background radiation. The images that we see of that, it's clumpy in places. Is there any indication that the James Webb telescope is seeing clumpiness in the early distribution of these red dots or early galaxies?
Yeah, that's an excellent question. So the technical word we use for that clumpiness is clustering. Do we see a clustering signal? And with the cosmic microwave background, you're exactly right. We see a very distinctive clustering signal. And we like to make plots of that signal as a function of like how big the clumps are, essentially. We call it the CMB power spectrum. And it's sort of one of the foundational facts of cosmology now. It really is one of the pillars of cosmology, and we get a lot of information from that. What James Webb is seeing is these galaxies, we think they are clustered or clumped together somehow as well, but we haven't measured enough of them yet to measure that signal yet. It's a subtle effect, and you need to analyse this in a statistical way. It's not like, we're looking for a specific pattern on the sky, what is it people see in toast, like pictures of Jesus or whatever, right? It's not that sort of thing we're looking for. It's like this subtle pattern that, on average, how far apart are these galaxies from one another? And at the minute, we don't have enough to make that measurement. You probably need a few thousand to measure that signal. Now we do this for galaxies that are a little bit younger, galaxies in a little bit later in the universe. We've been doing that for many years, and I've got a PhD student working on that right now. That's something we can definitely measure, but for these really super early ones, we need to see a few more of them before we can measure that signal. But we expect it to be there.
Okay, thank you. Great.
Does the spectrum from the little red dot contain anything, or is it just black body radiation? Is it just thermal?
Sorry, you might have to repeat the first bit, just because the signal was a bit iffy.
Well, little red dots, I assume a spectrum can be taken from them. Does that show any lines? Or is it just black body radiation, just a continuous spectrum?
Yeah, so are there spectra yet of... So right, one thing with James Webb is it's a beautiful instrument, everyone wants to use it. And so you have to apply to a big time allocation committee, and they decide who gets to use it for a bit and who doesn't. So I'm not sure if anyone has a spectrum of these little red dots yet. I think they must have, because some of them are a bit later on. And so you're exactly right that you would expect to see a particular type of spectrum depending on what they are. And for an accretion disk around a black hole, you'd expect to see something like, black body radiation and what we call a broad line emission. But I don't know, actually. I don't know if anyone's actually observed that, because that would be a nice almost a smoking gun signal. I do know of a paper where people have tried to make some measurements of this, and I think they found that it was consistent with that sort of emission, but I don't think that was necessarily spectroscopy and they saw a very clear signal. I think it's sort of people trying to use the data they've got and make some inferences. So I'm guessing that that's something people are very interested in doing if they haven't done it already. But I don't know of a specific instance, I'm afraid.
Okay, looking for one last question. I'm not seeing anybody, and I think at that point we should let Phil off the hook and wish you, and thank you very much for an excellent talk. Can you join with me and give Dr. Phil Bull a big Bexford Swinton Astronomical Society? Thank you. Thank you very much, sir.
Thanks very much, folks. It was really nice to be invited, and enjoy the rest of your meeting. Thanks very much.